So here's the problem we looked at in class. And it was about a company investigating fraud. They know that when there's no fraud, about 30.1% of the numbers of financial records begin with the digit 1. So if they're far from that, meaning way above it or way below it, then they know that they should investigate for fraud, do a more thorough investigation. Now this is important because they don't want to waste their time and resources investigating when they don't need to. So here in state, keep in mind state and plan are as if we haven't collected our data yet. In our problems where we tend to be given all our sample statistic as well, we would do this before we collected our data, state and plan, if we were really conducting the significance test. So we say we want to test the following hypotheses at the significance level. If you're not given one, we tend to use 0.05 or 1 in 20 as plausibility. Our statement of no difference is the null hypothesis, and it's always going to have an equal sign because that's what we're saying. We're assuming that this is true, and then we'd be basing our normal curve would be centered around that. And if our test statistic is far enough away, we can reject that, saying it's not plausible, and assume this alternative here, that it's not equal to 0.301. Now, we're concerned if it's way above or way below, because somebody might be fraudulently changing the numbers. And then we define what P is, the true proportion of expenses that begin with the digit 1. We always want to use Z for a proportion. Remember ZAP tax. Random condition. We have an SRS, so we know we have an unbiased estimator, meaning the center of our sampling distribution equals the true mean, the true proportion that had expenses beginning with the digit 1. Normal, now here this is an important distinction. Because we're assuming that 0.301 is true, we base our normal calculations on that. So we have to see that the sample size times P naught, which is this P sub 0 down here, that's what we're saying is the proportion from the null hypothesis. So we're referring to our sample size 300 times what we're assuming is true for our calculation, 0.301. That's bigger than 10, and 300 times 1 minus that is bigger than 10. So we know we have a large enough sample size in order to have an approximately normal distribution. We'd have to assume there are at least 3,000 expenses since we're sampling without replacement in order to use our formulas for standard deviation. So to do our calculation, now that we've checked conditions, we want to show what p hat is. 68 out of the 300 they found are begin with the digit 1. That's 22.67%. That could be far enough away. It's looked like that's a little under 8% away, 7.5% away from what we'd say they should tend to be. So we're going to see how far away that is in terms of our standard deviation. So our test statistic, remember that's just our z-score, or t if we're using a sample mean and we don't know the true standard deviation, is the z-score here, the statistic minus the parameter, so our value minus the mean over the standard deviation. So that's our sample statistic, 0.2267, minus the proportion proposed in the null hypothesis, 0.301, over the standard deviation of the statistic. And we get negative 2.8069. Normal CDF and calculate what's the probability that z is less than negative 2.8069. The thing we have to do here if we use normal CDF though is we have to double it, or if we use the table, because it's a two-sided test because of that not equal sign, because we're interested in it being far enough below or above that we're seeing that how often a value takes that value or one more extreme, and it can be on either side. So basically we're seeing the percent of values that are less than negative 2.8069 or greater than positive 2.8069 when z equals that. If you use your calculator, and this is why I encourage you to do that, stat test, one prop z test, it does that for you based on the fact that you put in a not equal sign. It doubles that p-value and it gives you about 0.0052. That means we would get this test statistic, 68 out of 300, less than about a half a percent of the time. So about 1 in every 200 times if the true proportion is really 30.1. So that's very unlikely and not plausible based on our significance level, based on most any significance level. So since our p-value is less than our significance level, that's alpha of 0.05, we reject our null hypothesis and assume the alternative. We have convincing evidence that they should investigate. Now, how does that relate to our confidence interval? Much here is the same when we want to do a confidence interval. Now, one key difference is to know that in confidence intervals, we're going from p hat to estimate the true proportion. So we say what we want to estimate in the confidence level. With z, just the same. Random condition is the same. The normal is not. So pause, look at this normal condition. It's not the same. It's based on p hat. Because in the confidence interval, we're using the sample statistic to estimate what the true proportion is. So we're using this, we're trying to find a confidence interval for the true proportion based on our sample statistic. The significance test, we went the other way. We assume that our claim is true and we see how likely the statistic would be. So here, the normal condition, we base this for confidence intervals on the sample statistic. Independent is much the same. Let's look at our test statistic. So here's our formula for our test statistic, or I'm sorry, not the test statistic, the confidence interval. So we have p hat plus or minus our critical value for 95% confidence times our standard deviation. P hat here is 0.2267, or here it's run until 0.227. So I'll fix that for clarity's sake. So this whole thing's our margin of error. Standard error is just the standard deviation. You can see the work coming down to solve for these. And we get 0.18 to 0.274. Now, what does that mean in terms of 0.301? Well, take a look at your confidence interval. Is the claim 30.1% included in the interval? No. That means it's not a plausible value. We're confident that the true proportion lies between here. For this reason, confidence intervals can give you more information. They tell you a range of plausible values where the parameter lies, or where we're confident the parameter likely lies. Whereas a significance test just lets you know to reject or fail to reject. That being said, a p-value being really, really small tells you how strong the evidence is or how far away it is. This gives you a little more detail, though, confidence interval. They were 95% confident the interval from 0.18 to 0.274 captures the true proportion of expenses that begin with the digit 1. Since 30.1% or 0.301 is not in our interval, it is not a plausible value, and the company should further investigate for fraud. So that's how the two are related. A two-sided test with an alpha value of 0.05 is equivalent to a confidence interval of 95%, because we're looking at 5% in either side of the tail. So just to sum up what we know about confidence intervals and significance tests, here's a picture. And this helps to really visualize it and be really, get the image down to understand what we mean. So let's look at a two-sided test. A two-sided test with a 5% significance level. So that means we're interested whether our test statistic lies down here, below z equals negative 1.96, or above z equals 1.96. So what we'd be seeing there is if p hat, for a proportion of p hat lies in this area. Now let's look at what that corresponds to in terms of confidence levels. So if 5% is the sum of the blue areas, that means 1 minus 0.05, 0.95 or 95% is in the middle here. So if we were in this blue region, half of that 95%, 47.5%, would be 1L. So if p hat is here, the lower bound would not be within our parameter. So our null hypothesis says this value right here in the middle along this line is our true parameter. It's claiming that's true. If we got a test statistic here, remember that it would be in the middle of our confidence interval, and the lower bound would not include that value. So for that reason, a 95% confidence interval corresponds to a two-sided test where alpha equals 0.05. Meaning, in the confidence interval, if the value is not included, the claim from the null hypothesis, then we would reject it. So in general, for a two-sided test, we could do 100 to make it a percent. 1 minus alpha tells us the confidence interval. 1 minus alpha gives us a proportion, multiply by 100 to make it a percent. So 1 minus alpha here was 1 minus 0.05, multiply, which is 90.95, multiply by 100 to get 95% confidence interval. Let's look at what it'd be for one-sided. Stop and think to yourself. For one-sided, it's going to be different if alpha is 0.05. This area altogether would be 0.05. So this is if our alternative hypothesis is less than for a one-sided test. Here we have 0.05 is that whole area there. So the corresponding confidence interval would be a little bit different. So if p hat was anywhere down here, let's look at what the confidence interval would be. So the confidence interval is centered around p hat. So if 0.05 is here, picture 0.05 also being over here. The area in the middle would be 1 minus 2 times 0.05, or 90% would be in the middle, not included. So half of that, 45% of our curve, is between the parameter from our null hypothesis that we're proposing and the rejection region where we reject our null hypothesis. So a 90% confidence interval, if p hat's anywhere in here, a 90% confidence interval in all confidence levels smaller would lead us to reject the null hypothesis. So this is a little bit different because we have to picture the parameter being 0.45 away, 45% away. So a confidence interval would be 0.9 here, a 90% confidence interval. If p hat is in this blue region, a 90% confidence interval would also lead us to reject. So a 90% confidence interval corresponds to an alpha level of 0.05 for a one-sided test. So in general, 100 times 1 minus twice alpha to get the confidence interval there. And that's because the p-value is all on one side. It's not split between the two sides. So to do this, what I would always do too is one-sided, all the p-values there. So this is 0.05. Now the confidence interval, you look at what's in between, what's not included in those. So that'd be 0.05 over here. So 90% is in the middle. That means this from the parameter for our significance test, our proposed parameter to the rejection region would be 45%. So confidence interval, p hat's here, it would have a 90% confidence interval, would not include this area for the upper bound, and the lower bound would extend over here into this area. On the other side of things, if our rejection region was up here and the p-value was up here, it'd be the same thing, but the lower bound wouldn't capture it. So if a confidence interval doesn't include the value from our null hypothesis, we would reject the null hypothesis. That's how they're similar.